Good morning, ma'am. This is my sixth chosen report, the determinant of a matrix. For this lesson, we have these following objectives. Number one, find the determinant of a 2 by 2 matrix. Second, find the minors and cofactors of a matrix. Third, use expansion by cofactors to find the determinant of a matrix. And lastly, find the determinants of a triangular matrix. So the determinant of a 2 by 2 matrix. Every square matrix can be associated with a real number called its determinant. Historically, the use of determinants arose from the recognition of special patterns that occur in the solution of systems of linear equations. For example, the system a sub 1 1 x sub 1 plus a sub 1 2 x sub 2 is equal to b sub 1. Another a sub 2 1 x sub 1 plus a1 a sub 2 2 x sub 2 is equal to b sub 2 has the solution x sub 1 is equal to b1 b sub 1 a sub 2 2 minus b sub 2 a sub 1 2 all over a11 a22 minus a21 a12 and x sub 2 is equal to b sub 2 a11 minus b sub 1 a21 all over a11 a22 minus a21 a12 when a11 a12 minus a21 a12 is not equal to 0. Note that the fraction has the same denominator, which is a11 a sub 2 minus a21 a12. So this quantity is the determinant of the coefficient matrix of the system. Okay, so definition of determinant of a 2 by 2 matrix. The determinant of a matrix A is denoted by that A or the absolute value of A or A sub 1 1 A sub 2 2 minus A sub 2 1 A sub 1 2. So given matrix A, which is this one, A is equal to A sub 1 1 A sub 1 2 A sub 2 1 and A sub 2 2. So to find the determinant of the matrix, this is the coefficient. This A sub 1 1 A sub 2 2 minus the A sub 2 1 A sub 1 2. The diagram below shows a convenient method for remembering the formula for the determinant of a 2 by 2 matrix. So again, we should always remember that the determinant is the difference of the products of the two diagonals of the matrix. So we begin with the main diagonal, which is this one. So A sub 1 1 times A sub 1 2, then minus A sub 2 1 times A sub 1 2. Example number 1, determinants of the matrix of order 2. So we have here matrix A, matrix B, and matrix C. So matrix A, 2, negative 3, 1, 2. So the determinant of A, let's have 2 times 2. So 2 times 2, then 1 times negative 3, then subtract. So minus 1 times negative 3. So 2 times 2 is 4, negative 1 times negative 3 is positive 3. So 4 plus 3, that is 7. Okay, for matrix B, we have 2, 1, 4, 2. So the determinant of matrix B would be 2 times 2 minus 4 times 1. So 2 times 2 is 4. Negative 4 times 1 is negative 4. So 4 minus 4, that is 0. For matrix C, we have 0, 3 halves, 2, and 4. So the determinant of matrix C is 0 times 4 minus 2 times 3 halves. So 4 times 0 times 4, that is 0. Negative 2 times 3 halves is negative 3. So therefore, 0 minus 3 is negative 3. Now let's proceed to minors and cofactors. So to define the determinant of a matrix of order higher than 2, take note the word is higher than 2, it is convenient to use minors and cofactors. So the definition of minors and cofactors of a square matrix. If A is a square matrix, then the minor represented by M sub ij of the entry A sub ij is the determinant of the matrix obtained by deleting the ith row and jth row column of A. Then the cofactor represented by C sub ij of the entry A sub ij is C sub ij is equal to the quantity of negative 1 raised to I plus j times M, or the minor, which is M sub ij. Okay, for example, if A is a 3 by 3 matrix, then the minors and cofactors of 2 of A sub 21 and A sub 22 are shown below. So first, let's find for the minors and cofactors of A sub 21. So, minors of A sub 21, we have here. The A sub 21 is here. So, therefore, by following the rule, delete row 2. So, we need to delete row 2 and column 1. So, the remaining values would be the minor, or M sub 21 is equal to A sub 12, A sub 13, A sub 32, and A sub 33. So this is now the minor of A sub 12. Now let's proceed to the cofactors of A sub 12. So C sub 21 is equal to the quantity of negative 1 raised to 2 plus 1 times M sub 21. Since negative 1 is raised to an odd number, so therefore it would be negative. So negative M sub 21. So this is the cofactor of A sub 21. Another, let's find for the cofactor of A sub 22. So for A sub 22 is located here. So following the rules, we need to delete row 2 and column 2. So the remaining values would be for the minors of M sub 22 would be A sub 11, A sub 12, A sub 13 rather, A sub 31, and A sub 33. So this would be the minor for A sub 22. Now let's have the cofactor of A sub 22. So we have C sub 22 is equal to the quantity of negative 1 raised to 2 plus 2 times M sub 22. So since the since negative 1 is raised to an even number, which is 4, so it would be positive. Therefore, that would be equal to M sub 22. So the minors and cofactors of the matrix can differ only in sign. To obtain the cofactors of the matrix, first find the minor and then apply the checkboard pattern of positives and negatives as shown in the right. So this one is the sign pattern for cofactors. for a 3 by 3 matrix. So we have positive, negative, positive, negative, positive, negative, positive, negative, positive. This one is for a 4 by 4 matrix. So we have positive, negative, positive, negative, negative, positive, negative, positive, positive, negative, positive, negative, negative, positive, negative, positive, and so on to an n by n matrix. So note that odd positions where I plus j is odd have negative signs, and even positions where I plus j is even have positive signs. Now let's proceed to example number 2. Minors and cofactors of a matrix. For instance, we need to find for the minors and cofactors of matrix A, which is equal to 0, 2, 1, 3, negative 1, 2, 4, 0, and 1. To find the minor m sub 1, 1, delete the first row and first column of A and evaluate the determinant of the resulting matrix. So again, for the determinant of m, or for minor m sub 1, 1, we have to delete first row and first column. So the remaining values would be negative 1, positive 2, 0, and 1. So therefore, the determinant would be negative 1 times 1 minus 0 times 2. So negative 1 times 1, that is negative 1, minus 0 times 2 is 0. Therefore, the answer is negative 1. So, to verify all the minors of this matrix, we could have the following. So, m sub 1, 1 is equal to negative 1. M sub 2, 1 is 2. M sub 3, 1 is 5. M sub 1, 2 is negative 5. M sub 2, 2 is negative 4. M sub 3, 2 is negative 3. M sub 1, 3 is 4. M sub 2, 3 is negative 8. M sub 3, 3 is negative 6. So how can we find for this one? Let's just follow the step in this previous example, which to find all the determinants of A will be following the process. Okay, now to find the cofactors, combine these minors with the checkboard pattern of sign 3 by 3 matrix as shown in the last slide. So therefore, we could have C sub 1, 1 is negative 1, C sub 2, 1 is negative 2, C sub 3, 1 is 5, C sub 1, 2 is 5, C sub 2, 2 is negative 4, C sub 3, 2 is 3, C sub 1, 3 is 4, C sub 2, 3 is 8, C sub 3, 3 is negative 6. Okay, now let's proceed to the determinants of a square matrix. The definition below is inductive because it uses the determinant of a square matrix in a square matrix of order n minus 1 to define the determinant of a square matrix of n. So, first definition of the determinant of a square matrix. So, if A is a square matrix of order n less than, greater than or equal to 2, then the determinant of A is the sum of the entries in the first row of A multiplied by their respective cofactors. So that is determinant of A is equal to the summation of A sub 1 j C sub 1 j from j is equal to 1 to n, or that is equal to A sub 1, 1 C sub 1, 1 plus A sub 1, 2 C sub 1, 2 plus dot 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 plus 2, or A sub 1, 2 C sub 1, 2 to A sub 1n, C sub 1n. So confirm that 2 by 2 matrix, this definition yields that the determinant of A is A sub 1, 1, A sub 2, 2 minus A sub 2, 1, and A sub 1, 2 as previously defined. So when you use this definition to evaluate a determinant, you are expanding cofactors on the first or in the first row. So example number 3. Find the determinant of a matrix of order 3. So for instance, we have this matrix A. So 0, 2, 1, 3, negative 1, 2, 4, 0, and 1. So this is the same matrix in example number 2. There you found the factors. There you found the cofactors of the entries in the first row to be C sub 1, 1 is negative 1, C sub 1, 2 is 5, and C sub 1, 3 is 4. So by definition of a determinant, you have the determinant of A would be equal to A sub 1, 1, C sub 1, 1 plus A sub 1, 2, C sub 1, 2 and plus A sub 1, 3, C sub 1, 3. So you need to expand the first row. So we have 0 times negative 1 plus 2 times 5 plus 1 times 4. So 0 times negative 1, this is 0. 2 times 5 is 10. Then plus 4 times 1 is 4. So 4 times 10, 4 plus 10 is equal to 14. So the determinant of this matrix is 14. So this is the same matrix in example number 3. So although the determinant is defined as an expansion by the cofactors in the first row, it can be shown that the determinant can be evaluated by expanding any row or column. For instance, you could expand this matrix in example 3 in the second row to obtain. So we have the determinant of A using the second row expansion. So we have A sub 2, 1, A sub 2, 1 times C sub 2, 1 plus A sub 2, 2 times C sub 2, 2 plus A sub 2, 3 times C sub 2, 3. So we have 3 times negative 2 plus negative 1 times negative 4 plus 2 times 8. So we have here negative 3 times 2, that is negative 6. Then negative 1 times negative 4, that is positive 4. Then plus 2 times 8, that is 16. To simplify, we have 14. So as you can see, it still produce the same result, which is 14. Another, in the first column to obtain the determinant of A, we have, or the determinant of A is equal to A11 times C sub 11 plus A sub 21 times C sub 21 plus A sub 31 plus times C sub 31. So let's use the first column expansion. Earlier, we have the row expansion. Here, we need to use the column expansion. So we'll have 0 times negative 1 plus 3 times negative 2 plus 4 times negative 5. So 0 times negative 1, it would become 0. 3 times 6, that is negative. 3 times negative 2, that is negative 6, plus 4 times 5, that's 20. So negative 6 plus 20, that is 14. So try other possibilities to confirm that the determinant of A can be evaluated by expanding in any row or column. So the theorem on the next page or next slide states this and is known as the Laplace expansion of a determinant after the French mathematician Pierre-Simon de Laplace, 1749 to 1827. So theorem 3.1, expansion by cofactors. So let A be a square matrix of order n, then the determinant of A is represented by or denoted by that A, or determinant of A, or the absolute value of A is equal to the summation of A sub ij times C sub ij from j is equal to 1 to n is equal to A sub I1 times C sub I1 plus A sub I2 times C sub I2 up to A sub In times C sub In. This is the ith row expansion. Or there is also um, jth row expansion. So we have the summation of A sub ij times C sub ij from I is equal to 1 to n is equal to A sub 1j C sub 1j plus A sub 2j times C sub 2j up to A sub nj times C sub nj. So when expanding by cofactors, do not you do not need to find the cofactors of 0 and 3's because 0 times its cofactor is 0. For example, we have A sub ij times C sub ij. So that would become 0 times C sub ij is equal to 0. So the row or the column containing the most zeros is usually the best choice for expansion by cofactors. So the next example demonstrate this. So for example number 4, the determinant of a matrix of order 4. So for instance, we have this determinant, we have this matrix A that is equal to 1, negative 2, 3, 0, negative 1, 1, 0, 2, 0, negative 0, positive 2, 0, 3, 3, 4, 0, negative 2. So notice that 3 of the entries in the third column are 0. So to eliminate some of the work in the expansion, use the third column. So we could have 3 times C sub 1 3 plus 0 times C sub 2 3 plus 0 times 3 sub 3 3 plus 0 sub C 0 times C sub 4 3. So the cofactors of C sub 2 3, C sub 3 3, and C sub 4 3 have zeros coefficient. So you need only to find the cofactor of C sub 1 3. To do this, delete the first row and the third row, delete the first row and third column of A, which is A, and evaluate the determinant of the resulting matrix. So C sub 1 3. So first row, third column. So we need to delete this one. So delete. So the remaining values would be negative 1, positive 1, 2, 0, 2, 3, 3, 4, and negative 1. So delete again the first row and the third column. So we have C sub 1, 3 is equal to quantity of negative 1 raised to 1 plus 3. So we have negative 1, positive 1, 2, 0, 2, 3, 3, 4, negative 2. Then we need to simplify. Expanding by the cofactors in the second row yields C sub 1 3 is equal to 0 times the quantity of negative 1 raised to 2 plus 1. So we have 1, 2, 4, negative 2. So therefore, following the rule, this would become 0. Then 2 times negative 1 raised to 2 times the quantity of negative 1 raised to 4. Then we have negative 1, 2, 3, and negative 2. So negative 1 times negative 2, that is positive 2, minus negative 3 times 2, that is 6. So therefore, 2 times 1, 2 times positive 1 times negative 4, because 2 minus 6 is negative 4. Then another, we have 3 times negative 1 raised to 2 plus 3. So we have negative 1, positive 1, 3, and 4. So therefore, since this one is raised to an odd number, which is 5, it will remain negative 1. So 3 times negative 1 times 1 times negative 1 times 4, that is negative 4. Then minus negative 3 times 1, that is negative 3. 3 times negative 1, that is negative 3. So therefore, negative 4 minus 3, it's negative 7. So to simplify, 0 plus 2 times 1, that's 2, times negative 4, that is negative 8, plus 3 times negative 1 is negative 3, times negative 27, negative 7 is 21. So therefore, negative 8 plus 21, that is equal to 13. So therefore, we can obtain the determinant of A, that is equal to 3 times 13 is equal to 39. Okay, let's proceed to the alternative method in solving the previous example. So an alternative method is commonly used to evaluate the determinant of a 3 by 3 matrix A. To apply this method, copy the first and the second columns of A to form fourth and fifth column. Then obtain the determinant of A by adding or subtracting the products of the 6 diagonals as shown in the diagram below. So this is what we call the basket method. So we have here A times A sub 1 1 times A sub 2 2 times A sub 3 3. This one, so we have here, plus A sub 1 2 times A sub 2 3 times A sub 3 1. So we have here plus A sub 1 3, A sub 2 1, and A sub 3 2. We have here. Then we need to subtract the another diagonal. So we have A sub, also minus A sub 3 1, A sub 2 2, A sub 1 3. There. Minus A sub 3 2, A sub 2 3, A sub 1 1. Okay, here. Then the last one, minus A sub 3 1, A sub 2 1, and A sub 3 3, A sub 2 1, and A sub 1 2. Which is here. As you can see, somehow it forms a basket. So this is what we call a basket method. So, and this 3, and we need to add these 3 products. So let's use the method, the alternative method in solving example number 4 or in solving this example. So again, we have matrix A 0, 2, 1, 3, negative 1, 2, 4, negative 4, positive 1. Again, we need to copy the first column, which is 0, 3, and 4. And the second column, which is 2, negative 1, and negative 4. So applying the alternative method of solving the determinant, so we have the following. So again, we need to add the products of this main diagonals, then subtract to the products of the second diagonal. So we have here, this one would be 4 times negative 1 times 1, that is negative 4. Then this one, negative 4, 2, 0. So negative 4 times 2 times 0, that is 0. Then we have 1 times 3 times 2, that is 6. Another, we have 0 times negative 1 times 1, that is 0. Then 2 times 2 times 4, that is 16. Then 1 times 3 times negative 4, it's negative 12. Now, by adding the lower 3 products and then subtracting the upper 3 products, you can find the determinant of A to be, so 0 plus 16 plus negative 12 minus negative 4, minus negative, the quantity of negative 4 minus 0 minus 6, that is equal to positive 2. So now let's proceed to the triangular matrix. So a square matrix is upper triangular when it has all zeros entries below the main diagonal. So as represented or illustrated here. So again, it is the entry below the main diagonal is 0. So this one, because this is the main diagonal. Okay? And the lower triangular when it has all zeros above the main diagonal. So here. So above this one. Okay? So the matrix or a matrix that is both upper and lower triangular is a diagonal matrix. That is, a diagonal matrix is one in which all entries above and below the main diagonals or the main diagonal are 0. To find the determinant of the triangular matrix, simply form the product of the entries on the main diagonal, since the above and the lower or the below values of the main diagonal is 0. So simply form the product of the entries on the main diagonal. It should be easy to see that this procedure is valid for a triangular matrix of order 2 or 3. For example, to find the determinant of A, okay, we have A is equal to 2, 3, negative 1, 0, negative 1, 2, 0, 0, 3. So as you can see, the main diagonal here is this one. Then the above or the below values is already 0. So expand the third row to obtain. So as you can see, all we need to do is to find the, or we need to expand the third row, which is this one. So we have 0 times the quantity of negative 1 raised to 3 plus 1. Then we have 3, negative 1, negative 1, 2. So it would become 0 since we have 0 here. Another, we have 0 times the quantity of negative 1 raised to 3 plus 1. Then the remaining values is 2, negative 1, and 0, 2. Then it would become again 0 since we have 0 here. Then plus 3 times the quantity of negative 1 raised to 3 plus 3. So the remaining values would be 2, negative 3, 0, negative 1. So we have here 3 times since the value is even number, which is 6, so therefore it will become positive 1. Then 2 times negative 1 is negative 2. Then 0 minus 0 times 3, that is 0. So 0 negative 2 minus 0, that is negative 2. To simplify, 3 times 1 times negative 2, so 3 times 1 is 3 times negative 2 is negative 6. So which is part of the product of the entries of the main diagonal. So as you can see, that 2 times negative 1 is negative 2, then times 3 is negative 6. So that is how to find for the triangular, the determinant of the triangular matrices. So the determinant of a triangular matrix is triangular matrix. So if A is a triangular matrix of order n, then its determinant is the product of the entries of the main diagonal. That is, the determinant of A, or equal to the absolute value of A, is equal to A sub 1, 1, A sub 2, 1, A sub 3, 3, 2, A sub n, n, considering that this one is the main diagonal. So for example, the determinant of a triangular matrix. So we have here the determinant of the lower triangular matrix. So as you can see, this is the main diagonal, and the above values is 0. So all we need to do is to follow the definition or the theorem 3.0. So we only need to do is to multiply or to find the product of the main diagonal. So we have 2, negative 2, 1, and 3. So 2 times negative 2, that is negative 4, times 1, that is negative 4, times 3, that is negative 12. Therefore, the determinant of this matrix is negative 12. So this would be an activity. So try this. So determine the determinant of a matrix. Exercise 1 to 12. So that would be all for my lesson on the determinant of a matrix. Thank you for listening and have a great day.